Hello everyone, I'm Lu Tanzao. It's my great honor to introduce our paper. The title of our paper is Exploiting Security Dependence for Conditional Speculation Against the Spectre Attacks. My presentation includes these 5 parts. Spectre vulnerability was first announced at the early of 2018. Speculative execution vulnerabilities become a serious threat to comedy systems, since speculative execution is widely adopted in most modern microprocessors. It receives many attention both from academic and industries. More important, its variants have been announced every several months in the past 3 years. Actually, the software patches are just an emergent reaction. Long-termly, we need to reconsider the architecture design for security. Spectre and Meltdown exploit the microarchitecture change caused by speculative operations and the lazy handling of exceptions. It has 3 key steps. First, induce the victim to incorrect the speculative execution path. Second, construct a long-time window for incorrect speculative execution. Third, infer the secrets from side-channel information leakage. This paper aims at a large class of realistic and dangerous Spectre attacks. They steal victim memory contents instead of the value of register and rely on shared memory to construct the catch-set channel. We have the following assumptions on an attacker. He can execute her code on the same version with the victim processes without evaluated privileges, and it is feasible for the attacker to induce the target branch to jump to the malicious gadget in the single or cross address space. There are several software mitigation methods. For example, insert reference to block speculative memory access, or reduce the accuracy of timer to prevent the speculative side channel. But they all sacrifice transparency and performance. There are 2 peer hardware mitigation methods, SpecLoads and SpecLoads. They allow speculative memory access by tracking speculative microarchitecture changes and updating them after resolving speculative states. But our paper demonstrates a different approach. We block the speculation instead of buffering their status. So we block execution for unsafe speculative instructions, but continue execution for safe speculative instructions to achieve a balance point. To capture the problems caused by safe or unsafe speculation, we introduce the concept of security dependence. Instruction J is security dependent on instruction I, with respect to leakage channel C if both conditions hold. I proceeds to J in program order. If J is speculative executed ahead of I, it will leakage information into channel C. Given the above definition, the table summarizes the major security dependence in Spectre vulnerabilities. In this paper, we focus on how to defend against the first 6 variants based on catch-set channel. We can find that security dependence comes from 2 situations, including memory-to-memory speculation and branch-to-memory speculation. Here, I take a 3-stage issue queue as an example. The matrix is used to check data dependence and edge information. It is also used to check security dependence. Once the instructions are selected to be issued, they will check the security dependence matrix. If it is the security dependent on other instruction, this instruction will be marked with the suspected flag. So we have a baseline design. We can block all speculative memory access. There are no microarchitecture change for speculative access. We can defend all existing POCs of Spectre variants, but it has severe performance degradation. Therefore, we propose the defense framework named as conditional speculation for better performance, which detects whether a speculative access is safe or not according to security dependence, and employs security hazard filter to recognize safe access and allow this safe access execution as usual and prevents the execution of unsafe parts from changing cache state. The first security hazard filter is cache hit filter. It consists a speculative memory size which hit in R1D cache is safe and continue execution, which means in R1D cache is unsafe and blocked. Judge whether an access hit in R1D cache, we can fill out access which do not fill new cache lines and deface exciting pieces of Spectre variants. Due to the high spatial locality of Spec CPU benchmark, the performance is improved significantly compared with baseline. But employed L1 cache hit filter, there are also significant performance overheads. So there are and more optimizations. Then we propose the second hard filter, trust page buffer based hard filter based on interesting observation through shared memory based cassette channel attacks. Spectre attacks need to speculatively access two page with data dependence. We consider this sequence of speculative instruction has as pattern behavior. There are at least two instructions, A and B. They access different memory pages. Instruction B has data dependent on instruction A. Instruction B results in an L1D cache miss. So we think they have as pattern. SPBuffer is designed to capture memory access behaviors with as pattern from all speculative executions. It records all the on-fly speculative memory access requests and checks their execution status. When a new memory request which miss in the R1 cache, SPBuffer compares its page address with its history records and it decides whether this new speculative instruction is safe or not. SpBuffer interface which access does not match as pattern and let it execute speculative filter out speculative access which has no opportunity to construct set channels. Let's put them all together. Baseline simple block out speculation. Cache hit filter run the speculative instruction which hit R1 cache. Furthermore, SpBuffer filter allow a speculation for portion of R1 cache miss request. For those which miss the as pattern, they are safe. They can continue execution. To handle the unsafe memory access, a straightforward policy is to block unsafe speculative access and bounce them back to BQQ when they wait for the clearance of security dependence before being reissued. In addition, inspired by event spike, we propose the SPBuffer hazard response. We employ the SpecLoads to retrieve data into speculative buffers deployed next to the private and shared last level caches temporarily, and does not update the caches until the access becomes safe. Differently from event spike, conditional speculation defeats most safe instructions by hazard filters and allows them to execute normally. For remaining unsafe instructions, we use SPBuffer to further reduce the performance overhead. We simulate an out-of-order processor with conditional speculation to evaluate the features in terms of performance on the complexity of out-of-order core. This table lists the key parameters of the simulated processor. This figure compares the performance impacts of three different mechanisms of conditional speculation. The naive policy causes the largest performance degradation. In contrast, CF blocking provides a certain degree of relaxing. By dynamically defining false security hazard, it allows the security instruction that hit R1D cache to be executed. The CTF blocking gets further performance improvements. Specifically, we see this benchmark case and RBM, this benchmark case have a greater improvement. This quantum have a less improvement. Majority cases, such as Hammer, have excellent locality, which succeed in providing data to pipeline and isolating subsequent execution. Buckets with low spatial locality mechanism have to short waiting time to retrieve data from memory. MLC has poor locality in caches as well. There are too many consecutive SpecLoads accessing different cache lines. We find that a small difference in performance impact between CF SPBuf for LLC and CF SPBuf for ALC. So we find that deploying speculative buf for ALC only is a better option due to its efficiency. All the benchmarks of Spec CPU 2006 with twin input size run on the settings with the 709 FPGA platform at the frequency of 50 MHz for the software suspense of conditional speculation. The benchmark case can run successfully without any modification. As shown in this figure, the performance height of CTL blocking on LPG platform is 2.8% on average. Based on CMYK 49 technology, we use synchronous ASIC design flow and tools to access the timing and error codes. We find that they are minimal. So we summarize the security analysis in this table. Both blocking and SPBuffer-based hazard response mechanism do not influence the defense ability for cache-side channel defense. As for hazard filter mechanism, CF defense against all Spectre variants based on cache-side channel. And the SPBuf filter is able to prevent widely used variants employed in shared pages, but fail to block variants that do not need shared pages. And we see the right figure. Existing Spectre type attacks are defensed, and several branch-based meltdown type attacks are also defensed. There are more contents in our paper, including details of microarchitecture design, security analysis for each method, and sensitive analysis on the complexity of out-of-order call. In conclusion, we propose the concept of security dependence and propose the defense framework conditional speculation. We have two failing mechanisms are invested to filter out falsely identified security hazards, and two hazard response mechanisms are employed, including straightforward blocking policy and speculative buffer mechanism. So that's all. Thank you very much for your attention.